Good morning. My name is Dr. Gonzalez Moya and I will be your general chemistry instructor. Today we'll be working with the titration lab, specifically acid-base titrations. In any chemistry lab, the safety measures are very important. A special attention today that we are working with a strong acid like 6 molar hydrochloric acids, and this is why we need to use PPE for protection in a lab, like goggles, a lab coat, gloves, and when we working with a strong acid, we use an apron also. And you need to pay attention in your surroundings because any problem with your colleague can be a safety issues. So pay attention today. The acids and base are used in many industries like food, pharmaceuticals, textiles, even in aeronauticals for electrochemical bath using in metal finishing products. Who can tell me what is acids and base? What is the definition of acids and base? Okay, one of the first definition of the acid and base is definition by Arrhenius. The Arrhenius definition tells you that the acid contains hydrogen, that when dissolved in water, he can form the hydrogen plus ion. This is a definition to the acid for Arrhenius, and in the case of the base, you have some base. When dissolved in the water, he produces hydroxyl radical, is OH minus. In this case, the definition of the Arrhenius predicts the behavior of many acid and base, but it's not good enough, has some problems. The H plus don't exist in water. So usually when this H plus react with the water, form the hydronium plus ion in water. This is aqueous, and this is some problem with the Arrhenius definition. Arrhenius also failed to explain why ammonia and potassium carbonate produce basic solution in water, but don't have hydroxide in their formula. That this is some problem with the Arrhenius definition. This is why we have other acid-base definitions that this is most widely used. Like this definition is called, because the scientists Bronsted and Lowry. We know in acid bases at Bronsted Lowry acid base definition. What is an acid? According with Bronsted Lowry definition, is a proton donor. So you have a molecule that has an ionizable proton in their formula. You have hydrochloric acid. These have an ionizable proton that can produce acid solution. When you dissolve in water, it produces the hydronium ion and the chloride anion. This interaction between the acid and the water, this is proton donor. What is the base? In the case of Bronsted-Lowry definition, it's a proton acceptor. The Bronsted-Lowry definition is about the proton, the hydrogen plus ion. This is a sector. In that case, when you have a Bronsted-Lowry base, ammonia, for example, interact with the water and produce the ammonium ion and the hydroxide anion. This ammonium have a pair of electrons here that can accept the hydrogen from the water to form the ammonium. In that case, the ammonium is a nitrogen with 4 hydrogen in the molecule, and the charge is positive. What is the difference between the ammonia and the ammonium ion? 1 proton, that this is accepted for the base, the bronze-telluric base. We see here in 2 examples that this is in water. Hydrochloric acid in water is an acid, and ammonia in water is a base. In these 2 cases, the water is acting also as acid and a base. In this case, the water is accepting a proton, is a bronze-telluric base, and in this case, the water is donating the proton to the ammonia. This is comporting as a bronze-telluric acid. This is the water is so important because now we see that he can act as an acid and a base. That you have the water can interact with itself, and this is calling the dissociation of water to produce hydronium and hydroxide. Now you have 2 molecules of water. One accepts the proton to form the hydronium, is acting as an acid, and the other water, this accepting is acting as a base, and now this is acting as an acid. From the dissociation of the water, we have an important thing, that this is called the ionic product of the water. That this is equal to the concentration of hydronium plus times the concentration of the hydroxide OH minus. This is a constant, and this is always equal 1/10 to the minus 14 in at 25 degrees Celsius in aqueous solution. What is this important for? How to know what is the acid and base? So the concentration that we use in the formula is molarity, that is capital N, and we define as mole of solute per liters of the solution. Okay. If this is always true for neutral solution, that this is distilled water, we have the concentration of the hydronium equal to the concentration of hydroxide equal to 1/10 to the minus 7. Now, for acidic solution, in the case of acidic solution, the concentration of the hydronium is greater than 10 to the minus 7. So in that case, you have greater concentration of hydronium that is related with the acid solution. In the case of the base, we are related with the hydroxide. The hydroxide is greater than 10 to the minus 7. That means now that the hydronium, according to the ionic product of the water, is lower than 10 to the minus 7. This is neutral, acidic, and basic solution. But these numbers, 10 to the minus 4, 10 to the minus 7, 10 to the minus 14, are difficult to handle. This is why scientists created the pH scale. What is the pH scale? This is very important when we're working with acid and base in general. In any lab or industry, we need to know the pH scale, but we will report solutions, acid, base, according to the pH. The pH is a relation minus logarithm 10 base of the concentration of the hydronium plus ion. Because we see before neutral solution, the concentration is 10 to the minus 7. This is equal 7. pH is 7. Now it's positive because this minus here convert the logarithm 10 to the minus 7 to 7. But now we have the same neutral solution. pH is 7. Acidic now related with before, the pH is less than 7. And in basic solution, the pH is now greater than 7 because always is related with the concentration of the hydronium ion, H3O+. Now we have the scale that usually go from 0 to 14, and 7 is like the middle point. We have neutral solution, distilled water here, and in this case, lower than 7, we have the acidic portion, and greater than 7, the basic solution. We have soda caustica is around 14, 13. We have the seawater around 8. This is basic solutions. We have urine between 5 and 6 is some kind of acidic solution. Blood is near 7. Gastric juice around 2. So this is how we define the substance that you use in every day as acid and base, and have many applications. You can use for cleaning in your house some acid solution, and this is also important. Now we define what is the acid and the base. We see what is the pH scale. Now what reaction we can do with acid and base. This is a very important reaction, that this is a neutralization reaction. If you react some acids, general formula HA, with some base, we can tell VOH as general formula. This is called neutralization reactions, and form water and a salt. This is a special case of double displacement reaction. You have the water is, you add the H to the OH, is the H2O. And in the case of the salt is the anion and the cation. This is better if we see real formula. You have hydrochloric acid reacting with a base, sodium hydroxide. This is acidic solution, a basic solution. You will form the water and the salt. This is sodium chloride, a common salt. In that case, now you have pH lower than 7, pH greater, but you finish the reaction with water and salt. This is more neutral reactions. You can get neutralization. In this case, a strong acid with a strong bases is getting a solution with a pH 7. And this reaction is very important for the practice today. We are talking about titration. Titration using the neutralization reaction to determine the unknown concentration of an acid or a base in solution using a base or an acid, depending what you start, to get to determine the unknown concentration. This is when the acid is neutralized, you get the stoichiometry of the reaction. Now the number of moles of the acid is equal to the number of moles of the base. So this is the equivalence point in the titration. We get this equation, but how we know when we end the titration? How we know when we reach the equivalence point. We use it. A pH meter is an instrument to determine the pH. When you get a pH meter, in the case of the titration, you can get a relation with pH, and milliliters added of the base. So if you start with the acid, the pH here from 0 to 14, start here, and this is the shape of the titration curve. You have a great change in the pH from acid to base when you add the amount of base. Now this equivalence point is around 7, and for this curve we can get the milliliters, the volume, the specific volume that we use from sodium hydroxide. So this is one way to do it. We know that this is important to get. Okay, the other way to get what is the finish or the end point of the titration is using indicators. What is indicators? Are substances that change colors when is present in acid and base. So you have different colors from the indicators. So in that case, you have some colors depending of the pH. That you have a sun that we have depending of the pH. You have some colors different change. We have different types of indicators. Methyl orange, methyl red, phenol red. We have, in the case of the indicators, the phenolphthalein will change the colorless in acid solution to pink in basic solution. The sense of the phenolphthalein is around 8, pH 8. We change. Okay, this is some pH meter that we use in the practice, and this is some electrodes that can detect the pH of the solution. And this is how to construct the titration curve that we see before. In the case of indicators, I talk about the phenolphthalein. You can see here in acid solution, hydrochloric acid, the phenolphthalein is colorless. We have no color in acid. When you have sodium hydroxide, a basic solution, you see the pink color of the phenolphthalein. This is how we track the change from acid to base to finish the titration. Is the end point when we use the indicators. The end point of the titration will be near to equivalence point, and we see from, in the special case of the phenolphthalein, when we see a light pink. Why? Because we need to catch the first change in color, that this is pink. Because if we add too much sodium hydroxide, we get now out of the equivalence point, and we will get errors in the titration. So here, this is the talk about the introduction, how you need to know about acid-base and titration for this practice. But how we use the actual equipment, we need to measure the unknown concentrations, and we use a measure of volumes. In that case, the titration is also known as volumetric analysis. Today we will get the titration of hydrochloric acid with the sodium hydroxide, that we know the neutralization reaction, that we get the water and the salt. We need to track specifically when the number of moles of this is equal to the number of moles of sodium hydroxide. But now we have the unknown concentration of the unknown concentration of the acid, but we know the initial volume. This is 25 ml, and we will start with a known molarity of sodium hydroxide, 0.1 molar, and we will get the volume that we measure by the titration. Now we have all we need to get the unknown molarity of the acid, the hydrochloric acid. But how we use this, we get the burette with the base. This is a special equipment to measure volumes, very accurate. You have here graduation from 0 to 50 ml, and here in the inlet measure we have the acid that we already add 2 drops of phenolphthalein to track the chain from the colorless to pink. In that case, we will add, now this is filled with the base, and this is in 0. We need to also pay attention how properly measure the burette. You have the meniscus of the liquid and need to be in the graduation, and you need to get the eye level in the meniscus. Now when you go down, you will stop your titration when the phenolphthalein change to pink, and you will measure the volume. In that case, the volume in the burette is always volume final minus the initial. In that case, we are starting 0, and already we get the measurement. But we not always start in 0, we can start in other number. The only care that you need to take is measure the volume, start volume, and final volume. Okay, I will show you how to do some titration. This, we use when we are doing actual experiment, we need to remember to take care of the safety measurements. In that case, this is important. We will add the sodium to the base slowly to try to don't pass the end point of the solution when you get the light pink. In the beginning, when you see the base hitting the solution, you see some pink, but this fades. This is why we need to gently stir the solution, because that is some formation of the base instantly, but will react with the neutralization reaction and will fade. And this is when we finish the neutralization or the titration, when we stir a little but the light pink don't fade. This is the stop, the end point. In that point you will measure the volume. So I will going, you need to go slowly and try to see if you get the color pink. You gently stir. Okay, we need to pay attention because we don't know the concentration of the unknown acid. You need to go in some point when you form more colors, it's almost there, but you stir and phase is not yet. Okay, you see now that form more color, but go away with the stirring. We are close, and now we need to go more slow. Some drops and stir again to try don't pass the end point of the titration. Okay, now when I feel we are close, we go drop by drop. Okay, this is what I told you about. Now I go drop by drop, but I pass the end point. Now this is too pink. We need a color more light than this. This is why this need to be pay attention, because now we pass the end point. We can take the volume, we stop in 24.9, but now because we pass the end point, this is some error in the concentration that we will get. This is why in the experiment we use triplicate. We do more trials to try to minimize that errors. And this is very important, why I tell you. We need to pay attention and be careful. But this is why in science we do everything more than one time, because you can get some error in the first time, but you will improve and you will better in the other trials. When you take average between 1, 2, 3 trials, you get less error. Okay, let's do the example how we analyze the results. We get the volume, the concentration of the base. The initial concentration is 0.1 molar. So at the base, we have the molarity of the sodium hydroxide, 0.1 molar. You have the volume that we get from the titration, 24.9 ml. We don't know the concentration of the acid, and we start with a fixed volume that I don't tell you, but we measure the initial volume, the 25 ml, with a pipette. The pipette is also for measure volumes very accurately. In that case, we start with 25 ml of sodium of hydrochloric acid. From this, we have all of we need to get this unknown. How we do, step by step. We know the concentration of the sodium, 0.1. Molarity is mole per liters. In that case, we use this as conversion factor to get the amount of using the volume. But here you need to change the volume to liters. That you start with the concentration is mole from sodium hydroxide. This is the molarity per liter the solution. Now you have the volume in ml, 25 ml of the sodium hydroxide, but because this is the liter, we need to convert milliliters to liters. We use the conversion factor from liters to milliliters. We remember 1,000 of milliliters is 1 liter. In that case, we can cancel the milliliters and the liters, and we will get, in that case, the amount of moles from in the case of sodium hydroxide. We get the 0.00225 moles. 0.025 moles of sodium hydroxide. Now, this is the first step. We have the number of moles of the sodium hydroxide. But you remember the neutralization reaction, you get the amount of sodium hydroxide react with the same amount of hydrochloric acid to get the water and the salt. This is the second step. You will get the number of mole of sodium hydroxide equal to the number of mole of hydrochloric acid using the equivalence, the stoichiometry of this reaction. In the case is 1:1, that you can convert with the conversion factor stoichiometrically. This is equivalent at 1 mole of hydrochloric acid, 1 mole of sodium hydroxide. This is from the reaction. Now we have the same amount, 0.0025 moles of hydrochloric acid. Now we have the moles and the volume. How you will get now is converting to molarity. You using the moles 0.00. Okay, in that case it's 249 because the volume is 249, and you divide the moles the liters. Again, you need to convert the milliliters to liters. In that case, you will get 0.025 liters. When you divide, you will get near to 0.1. This is 0.99 molarity in the case of the HCl. And this is the unknown concentration that we need to determine in the practice. We do 3 times and we take average and what is the error that we get. Okay, this is always important. I talk a lot about the errors and how we need to do 3 trials in general to better measurements. Now that you are prepared, you need to do your practice, your 3 trials, and report the results in the lab report. Also, I want you to think about the common errors in the titration experiment and discuss in your lab report. See you all next in other chemistry lab.